Hello everybody, Adam Lusek here, and today we're going to be talking about scaling test time compute, reasoning models, and ways of applying all of these ideas to open source models yourself. With recent releases of models like o1, previews of things like o3, Gemini's deep thinking model, Qiu32b here, DeepSeek R1, there's been a clear paradigm shift where we're starting to focus a lot of our resources in compute not so much on the pre-training portion of creating and running language models, but actually now towards the inference time or test time portion of it. So we're starting to see different techniques implemented, like letting models think for longer, creating much longer chains of thought, and working through problems in iterative reasoning ways. And it's pretty obvious now that putting a lot more emphasis and resources towards the test time compute of these models can really start to push a lot more performance. So today we're going to talk about what it means when we talk about scaling test time compute, some of the theoreticals around how to build models like o1 and the other reasoners that we've seen, as well as a few open source implementations for scaling test time compute on open source models ourselves that I ran some experiments with. To understand this a little better, it helps to get some context about scaling laws for pre-training. So looking at the popular GPT series, the models that power ChatGPT, if we look at the first, GPT-1, we can see that it was actually 117 million parameters. Following the release of GPT-1 was, of course, GPT-2, which came out in a few different releases, but their biggest and most popular one was 1.5 billion parameters. And through scaling up to even more parameters, we saw increased performance. This increased performance definitely didn't stop with the release of GPT-3, which then went from a measly 1.5 billion parameters up to 175 billion parameters. And so this trend of pushing performance by scaling up the amount of data that was used to train, as well as the parameter size, certainly didn't stop, with things like GPT-4 having a rumored but unconfirmed roughly 1.76 trillion total parameters. A little specifics on that, it said that GPT-4 is a 16 by 111 or so mixture of experts model with about 220 billion active parameters at inference time. But the point stands that as we scaled up the amount of data and the amount of parameters, we clearly saw increased performance. And this trend was so clear that OpenAI themselves back in 2020 even released this paper, Scaling Laws for Neural Language Models, that essentially tracked that as we increase compute, data size, and parameters, our performance that we actually are able to gain and the quality of models that we're able to train tends to increase. But as we've started to see recently, there have been a few issues with pure pre-training scaling laws. The first is that building larger and larger infrastructures costs a lot of money. Companies like Meta have many hundreds of thousands of GPUs, which can cost millions, if not billions, of dollars to put together. There have been rumored talks of wanting or needing to race towards a trillion-dollar cluster or whatnot to continue up with these scaling laws. So scaling up pure compute costs a lot of time and a lot of money just in general, but then we started to see another issue pop up. We started to realize that the data sets of text that we've used to train these models, generally things like Common Crawl or internet data, is pretty finite and not growing at the rate that we need or the quality that we need to continue just pure brute force scaling. So we've seen what's been identified as maybe a little bit of a plateau when it comes to scaling pre-training. And I think this is pretty obvious if you look at something like the GPT-4 model that we've seen. GPT-4 itself was released over a year ago, and then the only major update then has been the release of GPT-4o. And while GPT-4o is a very capable model, we've also heard from some reports that scaling and training runs on the next state-of-the-art models, which are actively trying to be created, aren't necessarily going as well or to plan as expected, or they have been for the last few years. This has forced AI labs to think a little bit more creatively about how they can start to push performance from subsequent language models, and so we have seen some improvements in things. More specifically, we see a bigger emphasis in higher quality training data. So, taking those massive data sets of web data and filtering them down to only the best of tokens to train the models on. So, there's been data sets like FineWeb, which is more of a filtered general common crawl, and also some task specific ones like FineMath, which is more just high quality math data. And training smaller models on more quality data has been very successful. We've certainly seen Meta take this up with their Llama models. Their most recent 3.370B Instruct has been outperforming, if not on baseline, with even their 405 billion parameter model. There's even been successful implementations of using synthetic data generated by language models themselves to assist in and have positive results in subsequent fine tuning and the creations of these models. And so, with these other methods of helping out with the training of these models being relatively successful, we're starting to see most models hover around the mid tens or teens up to roughly the 150 billion parameter stage, rather than ballooning up to trillions of parameters. But with these limitations of scaling train time compute and diminishing returns as models get bigger, we've also seen a shift to thinking about the other side of the equation, the inference or test time compute, and seeing what we can do with scaling that up. The idea here is very similar to how we actually reason through and solve problems. And that is that if you spend more time actually thinking on a problem or spend more, brain power per se, reasoning through a problem, it's likely that you're going to land on or think up or work towards a better final answer than just immediately responding with the first thing that you think of. This idea has already sort of been thought through with different advanced prompting techniques. We've seen things with few shot prompting of actually giving examples to a model or additional kind of information at inference time of the task at hand, and then more popularly, the chain of thought idea, or having a language model through prompting reason through a little bit more of the problem, and through spending a little bit more time generating and less directly answering, tends to increase the performance of answering a given question. And I'm sure for anyone who uses language model interfaces like Claude or ChatGPT a lot, you'll know that generally, especially for things like coding, you're usually not going to get the best first output on the first try. You'll usually have to go through some sort of multi-turn dialogue, refining down to a better or correct answer. And so the idea of spending more of your resources towards the actual generation step of the language model to improve performance is kind of what we've landed on with scaling test time compute. This falls into roughly two buckets. There's the fine-tuned and learned reasoning ability that models like O1, O3, and Q can actually do, and then there's a few other methods that are more on the decoding side, or when a language model actually generates, doing some sort of intermediary search or verification on those generations to better guide it. So let's talk a little bit about how each method is set up and implemented. The specifics around how models like O1, O3, and even some of the more open source ones are still a relatively close guarded secret, but through some available research and some other implementations, we can start to reason a little bit about some of the techniques that they might be using. The first step is generally thought to likely be some sort of supervised fine-tuning to make the model start to undergo and generate super long chains of thought. So what we're seeing here in this full chain of thought release from OpenAI versus GPT-4o is that obviously on the right here, OpenAI's O1 preview has output a much longer explanation and thought process per se here. And even in the background, our original query that we put into Q here, as we can see, the generated answer from it is quite the doozy. But it's been found that just fine-tuning models to create these self-correction, reasoning loops, and long chains of thoughts isn't enough to actually instill the behavior of reasoning into the model. This is where more advanced reinforcement learning techniques are actually used to instill the behavior rather than the imitation of reasoning into models. And the use of reinforcement learning for models like O1 is actually no secret. OpenAI is very public that they've used some reinforcement learning method to actually make the model perform complex reasoning. They just haven't given us the specifics. And there's a lot of different research out there for attempting this and trying it out, but one of the most successful and likely pointers in the right direction is the self-correct via reinforcement learning paper from Google's DeepMind, which is adequately called the SCORE paper. And the issue here that they are fixing with multi-step reinforcement learning that I noted a few sentences back is that the real shift here is that we're not actually fine-tuning the model for better accuracy or correctness per se, or being more right. We're fine-tuning it to be more correct in a process, or learn how to do this process. They've noted that here as saying that SCORE trains a model to not just produce the best possible response, but instead aims to train a model to produce the best final response in the final attempt. So this follows a two-step process. The first stage then is having a first attempt that is more closely aligned with the original model's response, but optimizes for the second response. This seems a little bit redundant, but essentially what we're doing is trying to force the model to learn to improve rather than jump to a conclusion or do sort of a initial pass that's more accurate. And this is meant to be more so a foundation for the stage 2, where we are going to learn more true self-correcting behavior. Stage 2 is then going to be initialized from this stage 1 of the training, and it's going to apply joint optimization on both the responses. So given the response from stage 1, we're going to be using reinforcement learning to hopefully get to the right answer in response 2. So this is going to be a bit of a modified reinforcement learning approach that uses a technique called reward shaping that instead rewards less the accuracy of the final response, which of course it does that too, but more so the improvement from the first response to the second response. And this will essentially shape the learning process to develop self-correction as a behavior within our model, which, as we can see, is an important thing to be able to do to better reason towards a correct final answer. And so this two-stage process where they train an initialization for self-correction by constraining first to the base model and maximizing the reward for the second attempt, and then having a stage 2 where they're doing the multi-turn reinforcement learning to maximize the shaped reward that takes into consideration the improvement from the first towards the second attempt, actually is able to greatly improve accuracy. So already, just being able to teach the model this ability to self-correct has the clear ability to improve its performance. And so some form of this and being able to learn this reasoning capability past just 2 turns, which is displayed in this paper, is likely what's going on in terms of these larger reasoning models that go back and forth for a while. But outside of doing this fine-tuning on language models to instill this longer inference time and reasoning capabilities, there's still a lot more that we can do with actually existing and open source models. So this will bring us more towards our decoding strategies or our generation-based search strategies, which we'll break down in here in a second. But Hugging Face has this wonderful blog and implementation, which I ran my own experiments on that we'll highlight in a bit, of scaling test time compute with open models. A quick note, I'm generally using the word decoding, not necessarily in the literal sense of converting the internal, logits into actual tokens, but rather the general sense of generating with the language model and coming to a final response. The best way to understand these strategies is to directly show them, so won't spend too much more time introducing, but what they mentioned that I kind of just went over is that there's kind of 2 main strategies right now for scaling test time compute. There's self-refinement, where models iteratively refine their own outputs or thoughts by identifying and correcting errors, which we just talked about, but then there's also this second part, search against a verifier. Search against a verifier, which they also mention here, relies then on generating multiple candidate answers and then using a separate verifier to select the best one. This is going to take the form of some search method, whether that be best of n or tree search. Now we'll break down 3 different methods in the implementations of these search-based inference time, test time, scaling methods. And the thing that I like about this is that these can be applied to pretty much any model out there. So you don't need any sort of large fancy fine-tuning or reinforcement learning pipelines that are heavily complicated. Quick context, all of the evaluations here are going to be ran on the Math 500 benchmark here, which is a subset of the math benchmark that OpenAI has as part of their research. So it's literally going to be the accuracy of being able to solve math problems. The reason I believe that math or different STEM fields and coding is a clear area of focus right now for these models and for these setups is because verifying math and verifying code is relatively simple. Math questions have a solution and they have a way to get to the solution. So we can very easily be able to verify these steps along the way, as well as a correct or wrong answer. This differs from something like a more open-ended humanities-based question, and we'll hopefully see, and we've seen with things like O1 and maybe with O3 once it gets generally released, that they're starting to be able to generalize their reasoning towards those, but there's definitely a clear bias right now towards math and coding for the reasons just mentioned. And that is, of course, because for a lot of reinforcement learning pipelines, or for what we're actually going to implement right now, we need some sort of verifier. And that's essentially going to be a model that can verify the correctness both of our final output or of the process that we're taking. And this is going to take the form of an outcome supervised reward model or a process supervised reward model, which was also popularized in more OpenAI research from 2023 in the Let's Verify Step-by-Step paper. The outcome reward model is going to be trained on the full step-by-step solution for a math problem, and then being able to accurately state whether or not the final answer is either true or false. And then the process reward model is going to be trained on labeled steps for the entire solution, where each step is labeled as positive, negative, or neutral in this case from their original data set. And then it's going to be able to give a score for each step along the way. And we can then use these models to apply a few search-related algorithms, where the general approach is we're going to generate either full answers or steps towards an answer, and then use both these outcome reward models or process reward models to either choose a best answer or guide down towards generating the best answer. As a baseline for where all of these comparisons are going to be, we're going to be looking at simple majority voting. Essentially, we're going to be generating up to something like 256 candidates from a single question. So just answering the same question 256 times with a language model at a high temperature so that we get some diversity across our generations. And then we are going to look at the most generated output, and that will be simply our final answer. Which, funnily enough, just doing this and generating up to 256 potential answers and choosing the one that comes up the most does actually just increase accuracy in general. So in and of itself, this is pure test time scaling. But taking this one step further, what we can do is apply best of n with our reward models. Essentially, it's going to be the same way of generating n independent responses, but this time we are going to select the one with the highest reward model reward as the final answer rather than the majority. This is meant to hopefully give us our most confident individual response, but it doesn't necessarily account for consistency. So along with the vanilla best of n, we'll also show the weighted best of n, which is going to aggregate our scores across all of the different identical responses. So we'll instead select the answer with the highest total reward. Essentially, this is going to prioritize high quality answers by boosting the scores through repeated occurrences. So it's going to take into consideration both the reward model's reward for the most confident answer, as well as the majority approaches for taking into consideration how many times that answer actually comes. From Hugging Faces testing, as you can see, as we go from just 1 up to 256 generations, using the weighted best of n boosts their model of Llama 3.21b, which they are applying these test time scaling methods to, up to almost the base accuracy of Llama 3.18b. So this is already showing clear improvements with just the weighted best of n approach here of generating n number, generally a lot, like 256 here, where it'll start to almost plateau, and then doing these weighted scorings with the reward models. But we have process reward models. So we can take this one step further by actually breaking it down into the individual steps used to solve the actual question at hand. We're still going to start by generating n number of candidates step by step for the math problem that we're solving. But then what we're going to do is we're going to look at the first step of the full steps and answers that the first generation actually implemented. We'll then apply our process reward model to score that first step. And then only those up to some threshold of high scores will be kept, and then the remaining nodes will be disregarded. We'll then expand out our tree here to generate multiple additional answers starting from those steps. And this will go on and so forth, where we'll generate a next full answer, check out the next step with the reward model, disregard those that get a low score, all the way until we either hit a base level where we can't go any further, or an end of sequence token. And so the theory behind this is that by allowing the process reward model to evaluate the correctness of our intermediary steps, we can use this beam search approach to identify and prioritize promising paths early in the process. So the step-by-step evaluation here is beneficial for a little bit more of those complex reasoning tasks where we might need or want to guide towards a more complex solution, rather than the best of n approach here where we don't necessarily do the guiding and rely fully on the model to generate the full solution. And the evaluated outcomes actually do back this up too, because what we can see now is applying beam search to the same experiment with Llama 3.21b versus 3.18b, we can see that we finally pushed it up to 2 to the 8 or 256 generations per problem to finally reach, if not surpass, the baseline performance. So it's already quite obvious that putting in a lot more of this inference time compute and scaling it up is starting to show clear, respectable gains in smaller models' performances like this. One final novel idea that the Hugging Face team introduced in this blog as well is actually the diverse verifier tree search method. Essentially, they're trying to solve the issue here where having one tree, if we get a really high reward on one step, can actually cause the tree to collapse in on that single node and not go off and explore other potential paths. So instead, what they do is they add one additional step where they split off the trees into multiple individual subtrees that are independent from each other. This is going to promote diversity and make sure that multiple different paths are adequately explored rather than just one single one. Which the hope here is that it will encourage the exploration of different solutions rather than just maximizing the reward that we're getting from our reward models. And thus show that at even higher compute budgets, we can push above our regular beam search in terms of performance here. But one thing you might note when actually binning all of these questions by difficulty level is that there's not one clear method here that's actually outperforming the other. We're seeing that majority voting at lower difficulties outperforms all of the other methods, but then at higher difficulties, we're starting to see things like the DVTS method start to shine through. And then in the middle, there's a mix of beam search and best of n. And this issue isn't actually something new. It turns out that there are optimal different approaches to how you're scaling test time inference based on both question difficulty and the actual compute budget that you have. And so there actually exists optimal scaling of test time compute based on question difficulty as well as your actual compute budget that can be applied to dynamically choose which strategy to use based on all of these factors. And so the Hugging Face team took from this paper and Google DeepMind's findings for this and applied it back to their algorithms here. And when scaling up the parameter size a little bit to the 3 billion parameter model, we're able to actually, with the compute optimal situation here, push performance of Llama 3.2 3B above the baseline accuracy performance of the 70 billion parameter Llama 3.1 model. So it's likely that labs like OpenAI are starting to use some of these ideas of optimal scaling for allocating more compute resources towards more difficult questions. You might see for easier questions, models like O1 think for less time than harder questions, where it will be stuck in this iterative thinking loop for upwards of many minutes. With Hugging Face's release of this blog, they also open sourced their methodology and repository for applying these search algorithms with the Search and Learn repo here. So I wanted to give it a shot and see if scaling test time compute on one of my models, like this ORPO Llama 3.2 1B40K model, would help improve any of its performance, as well as verify some of these Llama 3.2 1B results. So within their repo, they've made it very easy to recreate and augment their searching algorithms here. And in the recipes folder here, they have some quick examples of how to run the scripts as well as configure them with the YAML files and put things like your own model in to be assessed. So I ran 2 sets of all 3, the best of n, beam search, and DVTS algorithms, both on Llama 3.2 1B as well as my little guy over here. And let's take a look at what the results show us. Starting with Llama 3.2 1B Instruct, just to verify that their results are true. If we look at the best of n implementation, especially for something like this, where we can see that there is a little bit more complicated approach here, that as we get up and up, it starts to actually put together different responses, and then finally here at the end converges to the right response. With beam search, we can start to see a little bit more consistency with some of the more difficult questions where it might start off wrong at just the first pass, but as we explore the optimal steps, we start to converge more consistently on the right answers. This isn't necessarily always the case. Of course, this model, being a 1 billion parameter model, isn't necessarily the best at math, although it is pretty good for what it is. But we can see that in some cases where it doesn't necessarily reach the final answer of 90 degrees in this case, it will, however, be consistent in reaching towards what it thinks is the best path given the steps of the process. But contrary, if we look at something like DVTS or diverse verifier tree search for the same problem, we can see that widening up the diversity for this actually allows us to finally get to the correct solution here at the end at 16 generations. So having these independent subtrees and exploring those through scaled up compute actually does work. We can confirm that, at least for the Meta Llama 3.2 1B Instruct model that all of the original experiments were being run on. This definitely works with scaling up our test time compute given these different search and verification methods. So how does a model like my model, which is substantially worse in instruction tuning than Meta's instruction tuning here, actually perform? And this is what I was especially interested to see because this model is not good at math. It rarely is really even good at following instructions or the prompts that you show it to do. And you can see that because if we actually go along, a few of these don't even pick up the actual answers that the language model outputs. For something like this, where it's an intermediate algebra question, it starts talking about all sorts of random stuff. So even with a model that's not necessarily tuned for math or good at this instruction following thing, maybe if we throw enough resources and test time compute at it, we can get some accuracy. And surprisingly, the answer actually is that it worked. So in the beam search for this question 10 here, with this pre-algebra question, albeit it's pre-algebra, not necessarily the most advanced question, we can see though that at 1 generation we're still not hitting, all the way up to relatively at 4 generations. And then finally, under our weighted scoring at 8 and 16, we are starting to actually answer the correct answer of 4. For some reason, it only wanted to output 4 as green, but a green 4 is the right 4 nonetheless. To further see even if any of these methods could also help, but maybe it wasn't necessarily formatting it the right way, I did look back into the raw data here, and there were actually a few other correct answers. In the DVTS approach on question 7 here, which is a number theory question, for some reason, after outputting a whole lot of garbage, right at the 16th generation, it just straight up says the correct answer of 27. So maybe luck, maybe a little bit of not, but it got it right nonetheless. Best of N actually was also able to surface at least one correct answer. So we can see here that the correct answer is Evelyn, and on completion 80 all the way down here, we can see that it actually correctly notes that Evelyn has the greatest average speed before wandering off into a whole lot of nothing and talking about dates. So while my own language model isn't necessarily pushing the boundaries of frontier math, this does go to show that test time scaling can actually work even for suboptimal small models. I threw about $10 worth of compute uploading this onto a cluster of 2 H100s and ran it through all of these, and eventually, given enough time and enough generations, we were able to actually surface the correct answers, which, as we can see, with much more capable and well-trained models, is a lot more effective of actually converging then onto the correct answers. So at the end of it, this is really a new and novel approach and paradigm for scaling up a lot of these different approaches towards language models, both being able to instill reasoning and long chains of thought into existing foundation models, as well as augmenting through search and verification with these different search methods. And obviously, there's really something here. We've seen incredible performance come out as the evaluations of the soon-to-be released O3 model, and even just the currently available O1 models, as well as even applying to super small models like my very poor one, the ability to actually be correct once in a while, or things like 3 billion parameter models starting to become as good, if not better, than 70 billion parameter models. So really it's clear that this trend for allowing large language models to reason through and explore a wide range of possibilities to approach or solve a problem is directly correlated, at least right now, to improved performance or accuracy. And while there's many more approaches to actually implementing things like these than I covered in this video, this will be an interesting trend to follow to see exactly where it goes and how far we're able to push the performance given scaling up of test time compute. So with that being said, I hope you learned something interesting. If you like the video, like the video. If you have any questions, leave them in the comments below. And if you want to support the channel, consider subscribing. Thank you and have a great day.